step towards this research. So my presentation today will only cover the the testbed part. So we didn't explore the adversarial environment yet within the testbed environment. But yeah, let me start my presentation. So we came up with an idea that GNSS jamming and spoofing is pretty common nowadays, and it's increasing, proliferating basically with time. We have seen some significant GPS spoofing around 2024, and the table on the right shows like the number of flights that has been spoofed based on each country's, and the trend has been rising. So the same source also showed that the current trend or the amount of spoofing going on based on some locations. So we saw that these two locations are like highly spoofed or jammed region. One of them is the Eurasia region, so close to the Black Sea. As you can see, the circles represents the number of spoofed flight, and the plots for the hexagons where with red and yellow regions, it's representing the amount of jamming going on. So the left two are for the Eurasia region, and the right two are the around the Southeast Asia region. I picked these two because these two seems like the highest in the website they shared. They actually showed not really real time, but kind of recent data, which is this data is actually taken on December 12th, and it shows like how many which region has higher chances of spoofing. So before I dive into detail about talking about the problem, let me just recall how jamming and spoofing works. But thanks to Fayaz, because he actually covered a lot in detail this part, so it helped me actually. So yeah, normal operation for GPS signals works with the aircraft GPS receiver receives the PNT data, the position, navigation, and timing information from the constellation satellite through multilateration techniques. And if there is a GPS jammer acting as the radio transmitter, on generally is based on the ground, so it transmits a high frequency noise or interference signal on the GPS frequency band, the L1 band. It can create jamming, and as a result, the aircraft GPS receiver loses the satellite signals. How GPS spoofing works is basically, again, I'm kind of recalling what FIRE says. There's a higher, stronger spoof signal that overpowers the satellite signals. So during GPS spoofing, another ground-based or a group of transmitter usually begins to send some fake GPS signal, causing the receiver to actually calculate the fake position, time, and altitude information. Since the satellite signals are intrinsically very low power, so the spoof signals overpower these quite easily. So the GPS aircraft receiver now actually takes the fake signal as true and begins to share the new false position within the aircraft. So this is how jamming and spoofing works. Again, I'm not going into detail about how jamming and spoofing works or what type of jamming and like the different types of spoofing. We're trying to focus on the gap with the existing work. Speaking of existing works, there have been recent works where they actually focused on finding some end-to-end simulation with some algorithmic centric solution, meaning like they're trying to devise their problem and solve their problem within some using some algorithm basically. And there are also existing research that worked on detection mechanisms where they rely on limited observables, and there are some experimental setups. But having said those existing works, there are some existing problems or existing gaps that I would like to highlight is that intrinsically our GNSS signals are unauthenticated. The current works lacks hi-fi simulation framework, so no realistic hostile environment testbed exists that can emulate the complex GNSS attack scenario. And even there is, it is kind of, if you have to execute that, there are issues of regulations, so there needs to suffer from compliance issues. Also, there are a lack of open, scalable, and high fidelity simulation frameworks, and there are shortage of empirical GNSS dataset that capture realistic or almost near realistic aircraft dynamics, noise, and adversarial condition that could be used for ML detection. So this is where we are actually targeting. So our proposed solution is to implement a realistic, reproducible, and legally compliant cyber physical GNSS testbed yeah, in order to achieve the goal of this research, which is to develop a testbed that produce high quality, scalable, and experimental valid data to support and validate security studies for aviation systems. And I already mentioned the constraint for this presentation, not the research, is the integration of jamming and spoofing, because that is going to be our future step. So speaking of the test bed, so this is how our system architecture looks like. Here it consists of mainly four major components. One is the flight simulator called Blue Sky. Another is the signal generator called GPS SGR simulator. The third one is the receiver. And finally, we have an analytics block. So what happens is we run the Blue Sky simulator. I will show you the demo in the next slide, but before that, let me give you a high level what this architecture looks, how the architecture actually works. So the Blue Sky generates some trajectory data containing latitude, longitude, and altitude value, and it feeds the data to the signal generator. And the signal generator uses the ephemeris data from the archive satellites in the form of BRDC files, and using those files, they actually generate or create simulated IQ samples. So these IQ samples are transmitted towards the receiver, and the receiver uses something like called a config file, which actually determine like how this receiver will work to create output in the form of a MATLAB file, which contains mainly the GNSS measurements, values like the position, velocity, time, the signal quality, as in like carrier to noise density, dilation privacy, etc. And at the end, we try to analyze those values and try to get some plots to validate this testbed. So moving on to the first block, I hope you can see the video here. We have executed this Blue Sky simulation here. What we are trying to do is this is creating a realistic flight. I'm not sure if you can read it. I know it's a little bit blurry, so I tried to create the Dreamliner, the Boeing 787 Dreamliner, and it's flying from the location of the LAX, which is the Los Angeles airport, towards our Dallas Airport IAD. So I created the flight using the location of the LAX, and then I set like how it's gonna navigate as if you were actually flying the aircraft. And then I changed the direction. As you can see, the green thing is flying here, over here, yeah. And it's following the trajectory towards the destination, which is the Dallas Airport. So this unit, what happens after it executes this simulation, it creates a scenario file, which we actually used and modified and took used an orchestrator file can combine with the scenario file to actually generate CSV files. So the CSV file contains the main parameters like simulation time, the latitude, longitude, altitude. GA stands for the ground speed of the flight, and heading is basically the direction it's going towards. Moving on to the next block, what this Blue Sky feeds the data to is this unit, which is the signal generator unit. So how this works is we I mean, we actually design the input, the simulation input, with these parameters, where I will go through each of them quickly in the next slide. But for overview, so what it does is it combines the trajectory data and the FMS file as an input to generate uh, like a GPS signal based on the ground truth that is getting from the Blue Sky trajectory data, and then finally outputs the IQ samples that transmits towards the receiver, basically. So you can set what file you are using with the command of E. We can choose between dynamic mode or static mode. So both dynamic mode and static mode comes with two formats, either the art-centered, art-formatted XYZ format, where the north is the geographical north and X points um, towards the UTC center, and Y points towards the third direction, and or within in the format of latitude, longitude, and height format. So for this simulation, we worked with the static mode. So we supplied the simulation with fixed value for the latitude, longitude, so that we see that how the receiver is locked into that value. So in order to see, anybody has a question? Okay, never mind. So in order to see how the signal generator looks like, this is how um, the the input is applied. I know there's a bunch of code what you're seeing here, but let me go through one by one. So I have designed and set up the sampling frequency at 4 megahertz. The IQ quantization, I set it at 8 bits per samples. For the IQ samples, the carrier frequency was set on the L1 frequency band. Typically, the GPS L1 frequency band is centered around 1500 megahertz. The BRDC file, this represents the number 336, represents the days of the week. I have executed the simulation, excuse me, meaning like 336 is the days of the year. So it corresponds to around December, I think December 3rd, I forgot. 25 is the year that we are talking about, and N represents the GPS signal. So because GNSS consists of like other types of satellites, GLONASS and other Russian satellites, but N represents the GPS satellite. PRN, I think Fayaz again already covered what PRN is in detail, but for our overview, so it's using this unique identifier for the satellites to be matched with the actually this PRN is used by the receiver to be matched with the satellites that is trying to receive from. The input of this unit is the LLH that I already covered, like coming from the Blue Sky, and it usually outputs the IQ samples. As you can see, yeah, there you go. So yeah, the output. This is how the output looks like. It ran for around 48 seconds. And the duration can be set while encoding, but the output, as you can see, the first column represents the PRN number. The second and third column represents the azimuth angle and the elevation angle of the satellite, pointing towards what satellite it is. So azimuth angle, if someone doesn't know, is the horizontal angle from the north direction, and the elevation angle is basically this angle in the figure over here. Anyway, the third column represents the distance, actually the range in meter, and the last column is basically the signal power in ratio. So this is the generator block. Moving to the third block, which is the receiver block. So again, I'll run simulation so that we can see how it looks like. So just to recall, the GNSS receiver uses a configuration file to actually decide on how the observables will look like and other to set other parameters, and it will output different kinds of MATLAB files, which we will use for further analysis. So the channel actually gives us like the overall, or in short, I can say the different 8 types of channel files are generated stating the quality of each of the channel towards the satellite, and the final overall takeoff flight gives me the overall signal parameters and other required parameters. So this was able to lock in. As you can see, I supplied in the previous step as the latitude, longitude value, latitude value of 51.4, longitude value at 4.15, and height around this value. So I can see the receiver was able to lock in the satellite and get its original position, which is close to the ground truth value. Um, Moving on to the next step, which is so yeah, before moving on, let me highlight a few points, which is number one is the carrier to noise density, which are expected to be around the value of 50 dB hertz or more to represent a better quality signal, and I'm getting around 49, 51. So it looks like, depending on the channel, actually, because you can see the PRN represents different satellites. So each of the satellites or each of the channel has different carrier to noise density value in terms of dB hertz to represent the quality of each of the channels. And I already talked about the different output it generates. So there are 4 blocks inside the receiver: the acquisition, which actually detects which satellites or PRNs are present and estimate the code phase and the Doppler frequency. I think you already saw what Doppler frequency and code phases are. I'm not going into detail for that. The tracking unit actually maintains the continuous lock on each of the satellite signal, uses something like a delay lock loop to do code tracking and stuff like that. And the observable basically gave 7 observations, meaning like there are 7 active tracking satellites. There could be more channels, as you saw in the previous block. There were more than 8, but it was actually locking into actively 8 satellites, not all of them, as you see on the previous block. Anyway, moving on. So we already covered how the signals will go through and be received. So one thing that we need to be care about is the integrity monitoring, the RIM factor, which is very crucial in avionics. So the idea of this monitoring is to detect if one of the satellites is providing any inconsistent data or not. So typically we need 4 satellites to actually do the multilateration. But then again, here, in order to make, comply with the RIM integrity monitoring factor, we actually request around 5 satellites so that we can compare the pseudo range measurements, which is basically the distance to the satellites, and then to provide the validation based on that. We compute the horizontal horizontal protection level, HPL. And I think I will show you the formula in the next slide. But what happens is there are 2 parameters. One is called the required navigation performance, and the other one is called the actual navigation performance. We want the actual navigation performance within the bound of the required navigation performance, obviously. So if the HPL is within around 0.3 nautical miles, so horizontal protection level is basically, in simple words, is basically how far you need to keep your aircraft away from the nearby flying bodies, basically, to avoid any kind of disruptions. So this clearance is required. If violated, the system will trigger a loss of integrity alert. So I gave some formula. I'm not again going over. I think you already saw in a couple of presentation back how to calculate the pseudo ranges and how to calculate the geometric range in order to come up with basically the range from the satellite to the receiver. So moving on to the next slide. This is how we calculate the HPL, where we consider a scalar parameter and multiply it with HDOP, which is the horizontal dilution of precision. In other words, dilution precision gives us like how precise the value of the measured value is within the limit. So the less value it is, the lower value it is, the better the channel quality or the better the reception is. So in order to do the validation step, we will calculate two parameters. One is the position error, and another one is the velocity error in all of the three dimension X, Y, and Z. So this is how the formula looks like. And using this formula, what we got is this. So the red dashed line represents the ground truth. And I tried to use a box plot to actually show how the data is spread out and how far it is from the ground truth to have an understanding of how close we are or how narrow is the error margin is. So for easiness of reading the y-axis, the latitude value in degrees is around 51.42 with some error precision value, and the longitude value is around 4.15 within some error precision value. So which is comparable to the ground truth that we supplied initially from the Blue Sky unit, and also the altitude value is around that level, which is a little bit away from the ground truth, but again, that is a considerable amount. So next, moving towards the error plots. So this is how the error plot looks like. Just so everybody are on the same page, how far we are from the zero value is how more my error is. So the closer we are to the origin, the better it is. So as you can see, it's in the micro degree level. So the difference is very small, and we can say within our error margin. Similarly, we plot for the velocity as well, which is again very close to the error margin. The next plot we have is um, the the carriage noise density values for each of the satellite channel that we're being able to lock in. As you can see, it spiked to the desired value of around 50 dB hertz, but sometimes it going upper, like some of the channel having higher values, which is a good sign. But then again, there are some two dips we can observe here for PRN1, indicating that there were loss of lock during those times, and it kept on locking even afterwards when the other stopped locking. So all we care for now is to validate is if we're having the desirable carriage noise density value or not. Like I mentioned initially, as a future work, we will explore the existing attack types, the different types of spoofing and jamming model we have right now. We didn't dig deeper into that, but we have a plan to integrate those jamming and spoofing model. Once we have it, the different types of spoofing for example, let's say the meconing attack, the replay attack. I think Fayaz already explained what it is, but again, it's just basically what it does is send a copy of the same signal so that it does not looks different from the signal that is coming from the GPS. And there are different other types of spoofing: the nice spoofing, the coherent spoofing. Man in the middle is very common. I think majority of us knows what it is. And then we will try to investigate from different angles. We will try to realize what are the scopes, how to model them, what should be the injection point, and what should be our evaluation focus, like which parameter we should target for the evaluation purposes. So our expectation is we can target those two conferences. I know both of them are on the same time, but their deadline is in March, I believe. The first one, I have to check the second one. I'm not 100% sure, but we are actually aiming for that. If we succeed and we can get good the expected result, we will definitely go ahead and try to submit our work in these two conferences, at least one of them. So to conclude, I'm kind of reflecting what I already said. So far, we already developed a hi-fi GNSS testbed to generate some scalable work that can be used in research. For example, what you saw a couple of presentation back, like a neural network based detection model, or maybe we use different types of aviation research. So my testbed could be used and integrated with to make advancement in this research direction. We enabled end-to-end simulation from aircraft trajectories to GNSS baseband IK signals and receiver-derived navigation outputs. We produce some realistic synthetic data sets suitable for validating integrity monitoring and performance-based navigation analysis. So the analysis I was mentioning about the actual navigation performance, the ANP and RNP, actually comply this performance-based navigation analysis. We established a modular and reproducible framework that supports the systematic evaluation of GNSS receiver behavior under controlled or adversarial conditions. So our current limitation, as I'm mentioning again, is the attack integration, which motivates our future work on threat modeling and resilient evaluation. So I put the reference list at the end, but that's all from my side. If you have any question, I would be happy to answer.